Chapter 4, at least the first 3 sections, is all about rational functions. Yesterday we just talked about general properties, how you find the asymptotes. Today we're going to get into more with graphing. Finding asymptotes is still an important thing when you graph, right? But there's a couple other things that we need to figure out. So remember what we said yesterday. Vertical asymptotes are where the denominator equals what number? You get a vertical asymptote when the denominator is 0. As long as you don't have what? Because if you have this, you might have a hole in the graph instead of an asymptote. Yep? Right, common factors. So as long as, we said this yesterday, as long as you don't have any common factors, you will get a vertical asymptote. If you do have a common factor, you can get a gap in the graph that you can't see with the calculator. We call it a hole, right? It's so small that you can't even tell it's there. The only way you know it's there is looking at the original problem. So let's graph that function right here. Well, what value am I not allowed to use for x in that one? Yep.
Not allowed to use 1.
Right, not allowed to use 1. Now when I graph it, am I going to see a vertical asymptote at 1? Or is there going to be a hole at 1?
There would be a hole because it would just cancel out to 0.
So we're going to get a hole. And what's this graph basically going to look like? Like you're dividing two things that are the same.
It'd just be 1.
It'd just be 1. So this is basically going to look like the line y equals 1. And that's exactly what the calculator is going to show you. So there's your horizontal line. But we said that you can't use the number 1. So what it should really look like is something like, here's your line. You should have a hole in the graph at the number 1. That's how you would show it. How about this one? What value are you not allowed to use for x in that one? Yep.
1. Because then, like, you can have 0 divided by 0, but that's going to make a hole in the graph.
Right. We're going to have a hole because we have a common factor. That was going to be my next question. So we get a common factor. It's going to look, this one's going to be more of a slant. Okay, it's going to look like y equals x minus 1. If you were to divide it, you get one copy of x minus 1 canceling in the bottom, one copy in the top cancels. So it's going to look like y equals x minus 1 with a hole.
Do we need to put in our answer to this unit, like, that this function works only when x or y does not equal this number?
If they're asking, it depends what they're asking.
Okay, so I'm just asking, what's the function that can show the graph of, like, this, that, like, shows this function, then you simplify and everything. Is there any responses that you're going to need to, like, is there any question that you're going to need to say when x is not equal to this number?
You're definitely going to have to know what values you're not allowed to plug in.
Yes. Are there going to be any ones that you're going to have to put in the answer to have, like, a complete answer? As in, for this one, when x doesn't equal 1, it works. Or that there's a hole in the graph or whatever.
So yeah, you'd have to say if you plug in 1, there is a hole in the graph.
Okay. Yeah. So if it's asking this.
Yeah.
Okay.
Yeah. You'd have to tell me there's a hole in the graph. I might ask you the difference between a hole and an asymptote, definitely. Yeah. Okay, so in those first 2 examples, is it working for you? Yep, scan that. And your hole will close. So if there's no vertical asymptote, you get a hole. And we've been calling it a hole. It's not really called a hole. In math, it's called a removable discontinuity. The idea of something being a removable discontinuity means that it would be very easy to fix the break in the graph. So if you have something like this, very simple to fix that break. All you have to do is fill that hole in, and now it's connected. Right? Removable means it's easy to make it connected. If you have a vertical asymptote, something like that, and something like that, is there like a single dot that I could put somewhere that would make these two parts connected? No. That's a discontinuity because it's a vertical asymptote, but it's not removable. It's like it's not fixable. You can almost think of it that way. It's not. It's like you'd have to bend this piece back down and fix that and weld them together. Yeah, you can't fix that. Okay? It doesn't work. Okay? So the idea of a removable discontinuity is that we say, okay, you've got a function that has a hole in it. Let's go back to this one. Let's look at the first one. So we'll say that f of x equals, did you sign back in?
Do I just like
Just type it up already.
Yeah.
watch this guy here?
So this graph has a hole. If I want to fix it so that it doesn't have a hole, I could do this. Let me erase this so I got some space. Let's go like this. When I put this symbol, what kind of function am I doing?
Like a systems one where, well,
Piecewise.
Huh?
Piecewise.
Yeah, but can I explain like how it works?
No, that's okay. We don't have to do that.
Well, I just want to make sure I understand. So like, you do the piecewise for like x is greater than 5, and then for x is less than 5. There's like two. If there was two like lines, so there
Yeah,
was
you have different conditions on the domain.
yes, that's like that, right?
So for this one, if you wanted to draw this exact picture without the hole, I'd say you can use this one when x is not 1.
That
When x is 1, we've got to do something different. What do I want to do different? I want to fill in the hole. So what we graphed this earlier, what would I have to put here so that it would fill in that hole? Yep.
You could just do it like
supposed to
where it equals 1.
Yeah, it would just be 1. So if you're plugging in a number that's not 1, use this formula and graph it. If you're plugging a number that is 1, put a dot on the number 1. So what that would do is it would fill the hole in at 1. This is just graphing a single dot. That's what a number does, just a dot. So that's why we call it a removable discontinuity. So holes are removable, asymptotes are not. Any question on that?
Is that how you actually do it on the calculator?
No, you can't. I don't think you can graph a single dot on the calculator in like y equals. No. You can graph a dot on the calculator in other ways. You can actually turn individual pixels on and off on the screen.
Yeah.
But that's just turning pixels on and off. It's not really graphing in y equals. Yeah. All right. So let's say we had a rational polynomial. That would basically be something like that. You've got two polynomials. Usually you start with the highest exponent first, and the exponent keeps going down until you end up with a constant. Okay? And same thing in the bottom. Start with the highest exponent, then go down to the next one, the next one, the next one, until you end up with one that's a constant. What I'm going to be showing you here is an easy way to find the horizontal asymptote by ignoring all the stuff that doesn't matter. I basically did this with a homework question someone asked me about. I said you don't really even need to think about the +1 when you're getting numbers that are really big. Adding 1 doesn't do anything. The only thing that's really important are these first two terms. Does anybody remember what this term is called? We talked about it in chapter 3. It's what predicts what the graph looks like if you zoom out far enough. Yeah?
Oh, no.
Yep. Yep.
It's determines the degree, but it also it's like leading coefficient.
And it has a name. That leading coefficient was called it had 3 letters. Anybody remember? Yeah? N behavior model, yes. So this term, the first term, is the N behavior model for the top. The second box I did is the N behavior model for the bottom. Well, if you take the 2 and divide them, you get the N behavior model for the whole thing. Okay. So just a reminder, that term is the EBM for the top. That's the EBM for the bottom. And as x gets bigger and bigger and bigger and bigger, taking the highest degree term in the top and dividing by the highest degree term in the bottom is pretty much going to approximate what this function is going to do. Because if this first term is something like, let's say 8x squared plus 3x minus 5, when x starts to get in, say, the thousands, if you take 1,000, square it, and multiply by 8, right, that's a really big number. Plus 3 times 1,000 plus 3,000. Plus 3,000, that's not really that big. Not when you're taking 1,000, squaring it, and multiplying it by 8. So this other stuff doesn't matter. In the long run, it's too small to make a difference. Especially when x gets into like millions or the billions. This term is going to be way bigger than anything else. So that's why I say when x starts to get really big, the original function can be approximated by just the first 2 terms. Now, when x is small, that's not true at all. I'm talking about when x is in like the billions. Yeah.
Really quick question for the like hole in the graph. Is that similar at all to like the I thing we were talking about earlier about how you need to have a completely different graph thing to show like the square root of -1 thing, like for those types of numbers?
No, the whole doesn't have anything to do with imaginary.
But there is a type of graph that we don't have access to that like does show the thing for imaginary numbers.
Yeah, we're going to study something called the complex plane where we have a real and imaginary axis instead of an x and a y. Yeah.
Okay.
But
it's not this.
No, nothing with imaginaries in this unit. Yeah. All right, so this is the N behavior model for your rational function. Now, does anybody remember when you divide 2 things with the same base, what do you do with the exponents? Yeah, you subtract them. So essentially, it becomes x to the n minus m. Now, when you subtract, that could lead to negative numbers. We generally don't like to write an EBM with a negative number. So if you had something like 4 over 2 x to the 4th over x to the 3rd. That won't give you a negative number. Let's do it the other way. 5th. Well, you can reduce the numbers that are in front. So 4 over 2 reduces to 2. And if you wrote x to the -1 next to it, you're technically not wrong. You could start with that. But what does that really mean? X to the -1 means that the x should be where? Yep.
On the bottom.
On the bottom. So what I'm going to be looking for is that. So if that was your highest degree term at the top, and that was your highest degree term at the bottom, this would be the EBM. You just divide them. Any question on that? All right. So let's try this. Find an EBM and the horizontal asymptotes. So that's what the EBM does. It basically gives you a simplified formula to look at to find the horizontal asymptotes. And it ignores all the stuff that doesn't matter. Okay. What's the highest degree term in the top?
2x to the second.
2x to the second. What's the highest degree term in the bottom?
3x to the 3rd.
3x to the 3rd. And now when we simplify it, can anybody give me the final answer without a negative exponent? Just preferably if it's going to be negative, just put it in the bottom. Yep.
2 over 3x.
Perfect. That is called the EBM, 2 over 3x. Now the horizontal asymptote is what happens in the EBM as x gets really big. So HA is horizontal asymptote. What's going to happen to what's inside that box as x gets bigger and bigger and bigger?
Is going to approach but never touch 0 or
Yeah.
another number.
Yep, it's going to approach 0. Because as x gets bigger, the denominator gets bigger and bigger and bigger. And 2 divided by something bigger and bigger and bigger gets smaller and smaller. So it's going to approach 0. Make sure when I ask you for a horizontal asymptote, that is an equation. You have to write y equals, or if it was vertical, you'd write x equals. When you're writing an EBM, you don't have to write an equation. It's just an expression. EBMs don't have to have equal signs. Asymptotes do. Right, so if you told me the horizontal asymptote was 0 here, I give you half credit on the test. You got to put y equals. Okay, let's try this one. Okay, so EBM, highest degree term in the top. Yep. 2x to the 4th. Highest degree term in the bottom. Yep. Yep, always check the whole thing just in case they do it out of order. But I did put it in order. And when you reduce that, what do you get for an EBM? Yep.
It would be 2 over 3 because the x's cancel.
Yep. Now the horizontal asymptote might seem a little weird, but I'm going to ask exactly the same question. Tell me what happens to the number in this box as x gets bigger and bigger.
Stays the same.
So what is the horizontal asymptote? 2/3. Yep. So in that case, there was no x, so it basically just stays at 2/3. But it's still horizontal. And that's what we're going to study today. So if the exponent in the bottom is bigger, or the exponents are the same, you will always get a horizontal asymptote. If they're the same, the horizontal asymptote is going to be just the coefficients divided. If the one in the bottom is bigger, it's always going to be 0. Because all the x's in the top are going to disappear, and you're going to be left with an x in the bottom.
What if the top is bigger?
If the top is bigger, the simplest thing that can happen is you get a slant asymptote. And then if we start getting more complicated, you could get a quadratic asymptote or a cubic asymptote. You can start getting asymptotes that curve. And we'll do that tomorrow. All right, so how do we sketch these graphs? These are general kind of guidelines. They don't apply to every problem. Because not every problem has all of these things. So the first thing I recommend to try to find are asymptotes. Well, if you have a graph that doesn't cross the x or y axis, like this one, you're not going to be able to find the asymptotes. That graph never touches the x-axis, never touches the y-axis. But if it does, that's helpful to find. The next thing we want to try to find are the vertical asymptotes. Okay, vertical asymptotes, those are the zeros of the denominator. Once you get the verticals, you want to get the horizontals. Generally, there's 1 or 2 verticals in a problem. Only 1 horizontal, but you could have 1 or 2 verticals.
There's always one horizontal.
There is always 1 horizontal as long as the degree of the numerator is less than the degree of the denominator.
Yeah.
Okay, so what I'm writing right here, it only applies when the degree in the top is equal or smaller to the bottom. When it's not, then no, horizontal asymptotes go away. And then once we get the vertical asymptotes, like let's say you get a vertical asymptote at 2. We know that means you can't plug in 2, but you could plug in something close to 2, like 1.99, 2.01. We're going to check a number very close to the asymptote and see what happens. As you approach an asymptote, what usually happens to your y value? One of two things. Yeah?
It gets really, really, really small, but never that exact number. It gets smaller and smaller, but never reaches that number.
As you approach a horizontal, it does, but as you approach a vertical, it
either goes towards positive infinity or negative.
right. It's either going to curve up to infinity or down to negative infinity. It usually does something opposite on each side. It's possible it could do this. Could go up on each side. But usually the bottom one is more common. And then once we think we have the right graph, we'll double check it on the calculator. So I would say to graph these types of functions, you're usually going to need anywhere between like 5 and 9 points to plot and then connect them. You can always do more because we're going to use the table. So getting points is going to be very quick. Let's try to sketch this one. Okay. What's the degree of the numerator? Yep.
I'm sorry.
1. So we got a linear in the top and the degree in the bottom. 2. So this fits what we're doing. Degree in the top is smaller than the bottom. So let's figure out. Let's do the asymptotes first. I'll do the horizontal first. But to do the horizontal, I need the EDM. Okay. Before I reduce it, what's going to be my expression for the EDM? It will reduce, but don't do it yet. Yeah?
X over x squared.
It's going to be x over x squared, which reduces to 1 over x. Okay, so now I have a simplified formula to look at. That allows me to figure out my horizontal. What's going to happen as x gets bigger to the value in that box? Yeah, y is going to get very close to 0. Okay, so there's our horizontal. Vertical, that's a little bit more work. How do we find the vertical asymptotes? It's where, what? Zeros in the denominator. Okay, so we should try to factor that. If you can't, it's going to be like 1 in the homework. You have to use quadratic formula. But that factors. How?
X plus 2, x minus 3.
X plus 2, x minus 3. Yep. Which means how many vertical asymptotes do we have?
2.
We have 2. So vertical asymptotes. X equals, what's my first one?
2. Negative 2.
Negative 2.
Positive 3.
Positive 3. Okay, so we got the horizontals, we got the verticals. We can try to do the intercepts. So remember the rule for finding intercepts. The x-intercept is when y is 0. The y-intercept is when x is 0. Let's do the y-intercept first. All right, so y-intercept is when x is 0. If you plug in 0 in the top, what do you get?
Negative 1.
And what about 0 in the bottom?
Negative 6.
-6. So your y-intercept is going to be
1/6.
1/6. Okay, x-intercept. X-intercept is when you let y equal 0. Well, I don't have a y here, but what's representing y? F of x. So you put a 0 right there. If you do that, you have basically something like this. You have 0 equal to a fraction.
The only way it would work is if the top equals 0 while the bottom equals something else.
Right. The only way a fraction can be 0 is if the top is 0. And what number makes the top 0? 1. That's your x-intercept. Okay, so we got enough here. We can start setting up the graph with all that information. And then we're going to use the calculator to evaluate near the vertical asymptotes. All right, so let's put a vertical asymptote at -2, +3, and a horizontal at 0. It's okay. Y-intercept is at 1/6, so just above the origin, and the x-intercept is at 1. 1. Oh, no, I had that in the right spot. X-intercept at 1. Sorry. Well, that's not enough to go off of. I mean, I know what it's going to look like, but without doing some more points, if you've never seen one of these graphs, you wouldn't know. So let's get some more points, yeah.
So like, in the last homework, how it had like 3 intervals, and then it'd say like from infinity to -1, then -1 to 2. Is that kind of like, is it gonna curve the same way in the middle of those two asymptotes?
It is gonna be broken into 3 pieces, the graph, and it's gonna stay very close to the asymptotes in the middle. It's gonna be kind of like an S shape, and then we got to kind of see what's going on in these 2 sections. So usually, I think you almost made like kind of like tic-tac-toe, except you got 6 spaces. You're gonna end up drawing usually in like 3 of the sections. Left one, a right one, and the middle one. That's kind of how it's gonna work. So what we want to do now is make sure our table is set up to ask, and we're gonna plug in some numbers. What's a value very close to -2? Yeah?
-1.99999.
Okay, so that's just to the right. Just to the right of -2, you're going to be up at infinity. So we're going to be way up there. Right? I need a value to the left of -2. Yep.
-2.5.
A lot closer.
Not closer. -2.001.
Yeah, we want to go like really close. So when you plug in -2.001, that's not really -2, it rounded. You're at -infinity. Way down there. Okay. Now let's do another point over in here. I would say maybe like -8, -10, maybe just somewhere in there. See where we're at. So -8, we're at -0.13. So just under 0. And maybe we want to check -3. That might be another good one. -2/3. So -3, -2/3. Okay, that's enough that I can see what's going to happen in that section. All right. Now let's check near 3. What's a value that's really close to 3?
2.9999.
Okay, so just to the left of it, we're at -400. So way down. Just to the right of it, you're going to be way up. That's usually what happens. What would be another good value that I could check to see what's happening in this area?
7.
All right, it's +7. We're just above 0. So 1, 2, 3, 4, 5, 6, 7. That's pretty much, that's good enough. So remember, as you keep heading left and right, you have to stay very close to the horizontal. So you got to do something kind of like that, and kind of like that. As you start to head in, it's going to curve. It's going to start to run into those verticals, and it's going to go down to infinity and down to -infinity, up to infinity. So kind of like this. And same thing here. As you start to come in, it's going to curve. And go up. And the middle section, well, it's going to be trapped between the verticals. It is going to cross the horizontal. We have an x-intercept. That's okay. It's going to come down. It's going to kind of curve through those points.
Oh.
And go like that. Now, whether it's a little bit flatter in the middle there, or, you know, I might not have that curve perfect, but it's going to look pretty close. I thought it was a little flatter, but that's the idea of your graph. And that's a pretty typical graph when you have two verticals and one horizontal asymptote. That's kind of how it looks. Any questions on that one? Okay, but all these things are what really helped us to graph it. Maybe not, well, I guess the intercepts did help me too, because I tried to draw it through those points. Yeah, I pretty much used all that information. Okay, we have 2 more graphs. I should be able to finish them. Okay, how does the degree in the top and the bottom compare this time? They're the same. So when they're the same, you still get a horizontal asymptote, but it's not going to be at 0. It's basically going to be at the coefficient of the numbers divided. All right, so let's do our horizontal. To do that, actually, I'll put it up here. We really need the EBM. Anybody tell me what the EBM is going to be this time? Final answer? 3 halves. So knowing that, what's my horizontal asymptote? Yep, 3 halves. So even though the degrees are the same, you still get a horizontal. Once the degree in the top gets bigger, the horizontal goes away, and now we start getting a slant or even curves. Okay, so that'll be tomorrow. Vertical. Well, how do you find vertical asymptotes? Yeah.
By plugging y or f of x as 0.
That's how you find the x-intercept. You let y be 0. Which, in this case, I might not do, because to set this equal to 0, I then have to find where the numerator is 0, and that's a quadratic equation. It's not worth that much work to find the y-intercept. I can just plot more points on the calculator a lot faster. So I'm not going to do the y-intercept in this one. X-intercept I'll try to do, though, because that's quick. Yep.
Isn't it when, like, the zeros?
Of the
Denominator.
denominator. Set the denominator equal to 0. So, where are my vertical asymptotes here? Yeah. 5 halves is one of them. It's easier to think about it as a decimal just for graphing, so it's 2.5, 2.5. And there is another vertical asymptote. It's going to look very similar to the last one. Yeah. 0. So 2 verticals, 1 horizontal. We got an EBM. I'm not going to bother with the with the x-intercept, because I don't want to set this numerator equal to 0. I mean, maybe it's factorable. I don't even care. But I do want to find the y-intercept. If you plug in 0 for x, what do you get in the top? -4. And what if you plug in 0 in the bottom?
3x squared plus x squared. Bottom.
0. So where's your y-intercept? Where's your y-intercept?
Well, the thing is, like, it is 0 for the bottom, so if you say anything, if you divide anything by 0, is it that we don't have x?
Well, I'm not going to do the x-intercept. We might have an x-intercept. I don't know about that. But the y-intercept, yeah?
Is it like undefined?
Which would mean, can you break that down for me, make it simple?
0. I don't know how to break that down.
Yeah? We don't have one. Yeah. There is no y-intercept. This graph never crosses the y-axis. Okay. I got it. It can't cross the y-axis because the y-axis is a vertical asymptote. All right. That's enough information to start to make a sketch. Okay. What I do is I zoom out so it's easier for me to draw.
So when your vertical asymptote equals 0, then there's no y-intercept.
Right.
Okay.
Because you're not crossing that line. You never cross the vertical asymptotes in these problems. You can cross the horizontal, but you can't cross the verticals. Never happens. So we got 1 at 0. We got 1 at it's 2.5. And then we got a horizontal at 1.5. Okay, so there's your grid. You always want to get that set first. What did you get? Anything else? Nope, you just gotta plot some points now. Okay, so to plot points, you don't need a graphing calculator. You can manually plug in numbers for x. It's gonna take a while. That's why it's a lot faster to just use the table. Let's see. Make sure you use parentheses. Plus x minus 4 divided by 2x squared. I always type in the original. I don't use the one that I factored just in case I made a mistake. Make sure you type it in the right way. Go to your table. And you can leave those numbers there. If you don't want them there, you can delete them. Doesn't matter. Okay. Probably going to need at least 1, 2, 3, 4, 5, 6, 7, 8 points maybe to make a good sketch. All right. What's a good x value that's near this first vertical asymptote? We'll say just a little to the left of it. Yep.
Negative 0.001.
Sure. Negative 0.001. And you are at negative 8,000. So way down. Okay, if you did the last problem, you kind of already know what this one's going to look like. So we got that. What's a value that's just to the right of 0? Yep.
0.001.
All right, 0.001. When we type that in, we're up at positive 8,000. Now I need a value that's near 2.5, but a little smaller. Yep.
2.4 or 99999.
Yeah. So if you're just before the next asymptote, you're going to be way down. Right? And I've already told you this. Just after it, you're going to be way up. Now we need to check out a little bit more what's going on here. What would be a few good x values on that part of the axis? Yep.
Negative 8 like last time.
All right, we can do negative 8. So negative 8, 1, roughly. Right about there. I think that's enough for that side, just because we know what the last one looks like. It's just going to curve. If you want to get a little bit better idea of where it crosses the x-axis, I mean, you could try negative 2. I think it might be pretty close to where it crosses. Not quite. Negative 2 was a third. It's probably around negative 1.5. That's probably pretty close to 0. Yeah, it's getting pretty close. All right, so that left side's good. How about some values in the middle? Yeah.
Positive 1.
Yeah, positive 1, 1, 0. Oh, we just found an intercept. Because we found a nice intercept, it probably means we could have found those intercepts and it would have been factorable. if we chose to try to do it. All right, that's good for the middle. And now maybe a couple values on the right. I like to try to figure out where the curve is going to kind of bottom out, and then maybe one more point off to the right.
4.
4. All right, so we got 4, 4. That's a good one. So 1, 2, 3, 4. 1, 2, 3, 4. All right, so I can start to see where it's going to curve, and then I might do like 10. I think that's the edge of my graph paper. 10, 2. Right about there. It's the same as the last one. All right, so it's going to kind of stay really close. Start to curve. Remember, it just keeps getting closer and closer to those dotted lines. Up here, it's going to have that same curve. What's a little different in the middle this time is it's very steep. So what's going to happen there, it's going to be so steep, I think the calculator's it's going to have a hard time with it. So it's almost vertical. Just a little bit of a curve. And then it just keeps going down. So I don't think the calculator is going to be able to do the middle. It's too steep. Yeah.
Is there ever a situation where, like, in the middle it goes down and back up?
Yeah. There's one where you can get something that kind of has this behavior to it.
Yeah.
In the middle. Yep.
Because that would mean that both.
You could have something like this.
Yeah.
You could have something like that. Yeah. I think we look at one of those. There might be one of those in the homework, but you'll know if it does that because you just plot a bunch of points, and you're going to notice that you're down low on the inside and down low on the inside, versus being up high on the inside and then down low. So you'll be able to tell. Yeah. Okay. So if you look at the graph, again, I told you to have a hard time with the middle. It also didn't do the left side. It should keep going. Right? It doesn't stop. It looks more like what we did. Okay. Any question on that one? Yeah.
Okay, so the vertical and horizontal asymptote can be found by doing like the numerator and the denominator, like solving them out to find the two, like to find the zeros for that.
The horizontal is from the EBM. You don't have to find any zeros. You actually have to let x approach infinity.
Alright, and then for the vertical asymptote, you set the denominator to 0.
Yes.
Okay, and then the y-intercept, you just set all the x's to 0.
Yep.
For the x-intercept, you set the f of x or y to 0.
Yes, and in this one I'll do that because setting the f of x to 0 is very easy. I can very easily figure out what would make the numerator 0 in this case. All right. So last one, back to the first type where the degree in the top is smaller than the bottom. When you have that, it means you're always going to have a horizontal asymptote where? Yep. At 0. Yep. So, I mean, if you know that, you don't have to find the EBM. It's not like they're telling you to. There might be some problems where they do tell you to. But without the EBM this time, I can just tell the horizontal is going to be at 0. If you're not sure, find the EBM. The vertical, that's the zeros of the denominator. And the first approach we always want to try to use to find the zeros of the denominator is to factor. We always want to try to factor. I don't really want to have to get into doing a quadratic formula problem in the middle of all this. If I have to, I will, but I prefer not. Okay, how could we try to factor?
Since it's a, well, I guess, like, yeah, eventually figured it out that you can't, but since it's a minus thing, you would set it to x plus, right?
Whenever this is a negative, you always need one of each.
Okay. So
because you got to multiply two things to get a negative.
So I do like x minus 3x plus 1.
Uh,
If I'm like, it's not gonna work in the end, but just looking at the middle, because you need to like add them together to get negative 2x. Of course, they add together to get negative 2, which isn't negative 3, but it would work for the middle factor. Like if you're following the steps, and you're not looking at it like the entire thing, that's where you start, but then you figure out it doesn't work, right? Or are you supposed
That
to know
does
from
work.
the beginning that's not gonna work?
no, that works.
Wait, which one do you add and which one do you multiply?
Well, you FOIL. So you get x squared, and then you get plus x minus 3x, which is minus 2.
I thought it was like the two numbers need to multiply together to be the constant, and they need to add together to be the like 2x thing.
Yeah, in this case, they do.
Oh.
So that works. Yeah. So you factored it. So we get 2 vertical asymptotes, 3, and negative 1. So that's good. Perfect. I can do the intercepts this time because they're pretty straightforward. X-intercept is like when you let y equal 0. What's the only way, if you put a 0 in that box, that fraction would ever come out to 0?
If x equals negative 2, I mean positive 2.
Positive 2. So that's where it crosses the x-axis. Y-intercept. If you fill in 0 for x, what do you get? Yeah, 2/3. Okay, so we got enough information to start to set this up. Okay, so x equals 3. X equals negative 1. Horizontal at 0. What else do we know? X-intercept at 2. So, right there. Y-intercept at 2/3. And it's going to pretty much look, it's going to look like the first, well, all the ones we've done so far. All right, so I'll type it in. Again, always make sure you use parentheses when you put it in. X minus 2 divided by x squared minus 2x minus 3. Second table. Okay, what's a value that's very close to negative 1?
Negative 0.99999.
Yep. So we could do negative 0.99999, and we're up at 75,000. So way up here. If that side's way up, the other side is going to be,
Way down.
it's going to be way down. I can tell there's nothing different about this problem than the first two. If you're not sure, check it. Right? But you're going to be way down. And because that one is up and down, the other one is going to pretty much do the same thing. Okay, inside here, I'm going to be down. I'm going to be up. I just need a couple points to try to figure out the curve. I think the calculator is going to draw this one okay. I don't think the middle is quite as steep as it was last time. I think it's a little bit flatter. So I don't know. I think it might be okay. So negative 10, right about there. I like to get a point where it starts to do the curve. So maybe negative 3, about negative a half. So I don't know, maybe kind of like that in the middle. Something kind of like that. And then I would say let's try like 1, 2, 3, 4, maybe 5 and then 10. So 5 and 10. Quarter and 0.1. Quarter, lower. Let's see how the calculator does. Sometimes it's too steep and it looks like it just stops. But no, it did that one the way it should have. Okay, so that's sketching rational functions. Once you do one, they kind of look pretty similar. You can get a few different things that happen, so always just check near the asymptotes and make sure you know what's going on. Okay, any questions on that one? All right. Okay, so that's homework for tonight. We'll look at that tomorrow, and then we'll finish 4.2. And I'll put a list of topics that are going to be on the test.
Oh, can I share my last night?
Yeah.